Welcome to you all to a new edition of Fusion EP Talk. We have the pleasure today to host Aaron Ho, one of the few Canadians left in Fusion, and a PhD student at Institute ITER in the Netherlands. So welcome, Aaron.
Thank you, Alexis, for having me.
And maybe while people are still connecting to the link, you could tell us a bit about your background, your experience, and how you got into Fusion, and more specifically where you are today, and what's your main driver.
Yeah, okay, yeah, no problem. So I am from Canada, and I did my bachelor's studies in nuclear engineering. So this was actually the uranium reactors, not the fusion ones that we're studying now. And through that program, I ended up learning about, during the alternative energies course that we had to take about fusion, I ended up learning about it there. And sort of, it stuck in my mind. So even after I graduated from my bachelor's, I worked a few years in the nuclear industry. And then, I decided, oh, I want to try something new, and then that idea popped back in my head, nuclear fusion, let's see what that's all about. And then I ended up signing up to do a master's in Europe for that. And I liked it. So I stuck around and did a PhD as well. And yeah, for me, it's always been sort of cool, the idea of plasmas in general, because yeah, as soon as I found out that they were basically what makes up lightning, and the lightning bolts in the sky, I'm like, okay, that's pretty cool. It'd be nice to know what's happening there. So that was sort of, and the fact that we can use the same materials to do fusion and create energy, that was sort of like, yeah, it seems like a nice concept, let's tie it all together. And for me, it was more just like an interest rather than trying to change the world or save the world with energy production. It was just more like, oh, okay, that seems like interesting thing to know something about, so let's go there. Yeah. And then yeah, so right now I'm doing a project in the Netherlands on specifically plasma turbulence predictions, and trying to incorporate modern machine learning and modern computational techniques to those predictions. And yeah, for me, that was also an interest, because I've been working with models and doing modeling basically since I graduated from my bachelor's. I found that was really what I liked doing, working with computer simulations and tables of numbers. So it just seemed like a really interesting idea that we can now, with the new modern capabilities of computers, get the machine to do our work for us by just throwing numbers at it and then letting it decide what's going on. So that idea was very attractive. So I wanted to see. Okay, great. So yeah, thank you everyone for coming. I guess I'll give you a bit of a introduction to what's happening in terms of using machine learning in plasma turbulence predictions in fusion plasmas, which is the topic of my PhD. So I'm at DIFR right now, and I'm part of the integrated modeling and transport group at DIFR. And this project was proposed by my supervisor, Jonathan Citrin, because yeah, he just had an idea one day. Someone approached him and said, oh, well, you should try using neural networks to do what you do. And he tried it, and it sort of worked on a very primitive basic model. And from that spawned this project. So I'm going to explain to you what that is. But first, just a little bit of, very, very basics of what's happening inside a fusion plasma core right now. Is that, okay, if we have this plasma magnetically confined, with the charged particles kind of stay confined within the center of the vacuum vessel due to the Lorentz force. And the idea is that if we can raise the density and the temperature of the particles inside this confined plasma, then we get to a point where nuclear fusion starts happening, and the power that we produce from the reactor is proportional to the density and temperature squared. So ideally, we want the highest that we can get. without, well, okay, caveats, but let's say we want to optimize that and get the highest density and temperature in the core. Now, from experiments, we see that even though we have this magnetically confined cage, that the particles still somehow manage to escape the core due to other transport processes. So there's first they thought it was collisional, so that they came to, you know, diffusive models. Then they calculated that, found out that the diffusive models are not sufficient to explain how much energy is leaving the core. So they found out at the very end that it was due to this phenomenon called plasma microturbulence, which is sort of like a rearrangement of the plasma due to, you know, the enormous stresses that it's under. So to kind of even out the plasma, make it more uniform, because it's nature doesn't like having a lot of one thing in one area and nothing in the other area without a lot of strong forces keeping it there. So this microturbulence comes out of the collective nature of plasmas interacting with itself and having all this nonlinear effects. But we found that the behavior of microturbulence is really sensitive to local plasma parameters. So that's like the local density at a point in the plasma, the local temperature, and the gradients, and especially the gradients. So the higher gradients we have, the more turbulence we generally drive in the plasma. And so that's sort of the fundamental idea of how we're approaching trying to predict plasmas predict the turbulence inside the plasma, is by taking the local plasma parameters, running it through theories and various models to predict then the transport coefficients that result from the turbulence under those conditions. So just a bit of motivation is that the currently gyrokinetic theory, which is, you know, it's a theory of particle distributions inside the plasma and how they interact and move in space and under various conditions. This is the theory that's most widely accepted as the accurate model for core plasma microturbulent transport. But the problem with such models is that they take a long time to evaluate. So if you wanted to run even like a gyrokinetic simulation of the entire tokamak, you would take, you know, millions, maybe even billions of CPU hours. So like this is like even on the limit of what modern supercomputers can do reasonably. So people have taken the basic model and reduced it down, applied simplifications that are specific to the tokamak, and basically through those simplifications, we're able to speed up the code, you know, like 1,000,000 times. So now these reduced models can do the whole tokamak in maybe, you know, a few minutes. But of course they're reduced, so they only apply to certain situations. And even then, that's still not fast enough to use it in a predictive capability, because you don't need to only evaluate that plasma condition at one state, but a state evolving in time. So you need many, many evaluations to get how the plasma will move in time, and as you apply different things like heating and changing magnetic configuration and stuff like that. So it still needs to be faster. And then the idea of the neural networks came by, which reduced it even further. So we've had other colleagues of mine have come before me doing extensions of the neural network principle that my supervisor originally tried. And my project is primarily to extend that methodology even further by including more inputs and capturing more of the physics, basically more possible scenarios. So just to give you an idea of how we run our simulations then, where the neural network fits in, ignore the equations. They're mostly is the highlighted parts that I want you to pay attention to. So we have like a macro scale transport model, which tells us how the plasma behaves sort of as a fluid, and how the density and temperature and pressure and momentum transport through the device. on a more or less a 1.5D, so a mix between 1 and 2D range. But the idea is that from this model, we kept the local plasma parameters, which we pass into our microturbulence model, which then is a lot of complicated integrals and stuff like this. But the idea is that it computes the fluxes, basically the particle and heat fluxes, which then go back into the transport model, update the density and temperature profiles, and this loop continues until we are satisfied with the answer or until we can successfully capture the evolution of the plasma. So you can see that even though this model here is very fast in terms of absolute sense, it's only a few seconds to do one point. The fact we have to do this like thousands and thousands of times makes it then still not quite fast enough. So the current bottleneck for these types of models is the microturbulence model. And that's why we're starting there with the machine learning stuff. So the idea is that because of this, the structure of our models, we can actually, and the fact is loose coupled. So these parameters are passed from one module to another module, like one code to another code, basically through interface. And they're not simultaneously solving all of these equations at the same time. So they're passed back and forth in sort of like a sequential process. That allows us to remove basically one of the components and replace it by anything that would do the same job, which we call a surrogate. And that surrogate can be literally anything that takes the inputs being these plasma parameters like density and temperature and gives out, in this case, fluxes. And the idea was then to put a neural network there because neural networks, they're basically enormous fit functions with like thousands and hundreds of thousands of individual fit parameters that are capable of being an approximation to any function that exists under the sun. The only difficulty then is training it. So deciding what those individual parameters will be such that it takes the inputs and gives you the outputs you want. But in essence, that by putting this in here, we can effectively provide a surrogate that gives the same performance as the reduced model, but much, much faster. But the downside being that we need a lot of data to train the neural network because it doesn't automatically know what is the right transformation from the input to the output. And as my colleague Carl found out, that is not so easy as simply taking the neural network packages from the internet for open source packages and then throwing your data at it and hoping that the output is fine. No, you need a little bit of physics knowledge in designing that neural network, the architecture and designing how you train it and what type of data to give it in order for it to give a good prediction, because otherwise it can really emulate anything under the sun. Any sort of, let's say, relationship between the inputs and the outputs instead of the relationships you want. So that was I won't get into detail on exactly how that's done, but it is important. So for our cases, what we're doing is the microturbulent transport predictions, and these are the input parameters that we use. I won't go through them all listing them because they're all here, but the idea is that they're all local. So they're evaluated at a single point in the plasma, and then we can just take this set of numbers and treat it as one data point for our training set. And then we need to get the corresponding transport fluxes such that it knows which inputs, the machine learning algorithm knows which inputs correspond to which outputs and can find the connection between the two. So how we do that now is that we evaluate the original model, which is called QualiKeys, the quasilinear turbulence, microturbulence model that we have. So we evaluate it for each set of inputs and produce sort of like an input-output map. Just a whole bunch of data points that say, okay, if you use these inputs, you get these outputs. And then by running that model, I think we have about 100 million points. So we ran that model 100 million times to generate our data set. which is then used as the data set for training of the neural network. And then basically the neural network will loop through all those data points and slowly try to adjust all the individual fit parameters of the neural network to match all whatever input we give it will match, that it will then spit out the output that is corresponding to that input. So unfortunately, such a technique means that the training of the NN, so then the ultimate neural network at the end, will only be as accurate as the original model. So in this case, it'll only be as accurate as quality keys and whatever assumptions it has made in producing the results that it does. So of course, that is a limitation if we're using the reduced models, because then they apply only to very specific types of plasmas. But the advantage we gain is that it's orders of magnitude faster. So of course, we're still coming up with ideas on how do we reduce the amount of data that we need and still get a good neural network, because then we can use higher fidelity models, the models that take even longer to compute, but provide a much more accurate result, but use those models as the generation of the data, as the generator for our data set. Okay, but so this is the methodology. And so this is, I'm showing you just some results from my colleague Carol, who is the one who made the previous and current state-of-the-art neural network. So we have in these shaded regions, the experimental profiles, the experimental data from JET. And then in the solid lines is the prediction from the original quality keys model, the original microturbulent transport model. And then in the dashed lines is the results of the predictions from the neural networks. And you can see that, at least as far as we're concerned, that these two lines, the dashed line and the solid line, match pretty well. Of course, the simplified physics inside quality keys lead to some deviations from the experimental profiles. So that's, again, just showing you some of the limitations we had. If we had a much more accurate model, or, you know, if we were able to capture everything that the plasma is undergoing with one model, then these two lines would hopefully get closer to the experimental data as well. But the advantage is that now it takes, with the whole thing being the original transport model plus the quasilinear part, this entire simulation took 2 minutes to run, and it was 2 seconds of plasma. And if we use the original quality keys model, that would take about 2 weeks to run continuously on 16 cores. So you can see the speed up is phenomenal. And now with the neural networks, we can do exploratory studies. We can, you know, take a fresh discharge from the machine, run it in a simulation, and just see what comes out of the other side to start the analysis on a much better foot, rather than having to, you know, pick out, okay, how are we going to put this data in and how are we going to run the simulation? We can just run a bunch of them because they're so quick. And that's really the advantage. So I guess then from here, I'm going to go, that was sort of all background into my specific work, which is how do we increase then the amount of physics inside this neural network. And one idea was to, because of all the data we need, right? The previous network that I just showed you was generated with 100 million points. And we figured that we need to add a few extra dimensions, so a few extra inputs, input parameters, in order to capture the rest of the physics. But if you just do this naively, then because of what is known as the curse of dimensionality, each dimension you add starts to add exponentially more points to your data set. So we need to run even more of the quality key simulations to generate our training set. And this was not desirable because 100 million points already took quite a long time, like a few months to generate. So we want a very intelligent way of reducing how much data and where it comes from, reducing the set that we need to simulate with the original model before we get a good neural network. And one idea that came up with was to basically start with the experiments, take experimental profiles or experimental data and use those to sample the space, the input parameter space that you need in order to get the training set that you want in the end. But the problem with this was that, well, experimental data doesn't really fit into a model easily off the bat because it's irregular. The data points don't have no information about the gradients. The data points don't always agree with each other either. There's a lot of error inside with error bars. So it's hard to use the data exactly as it is inside the model. But if you fit the data, then you get these smooth profiles, which then you can get the gradients. You can even look at the error of the fit to sort of figure out exactly what sort of inputs you need. So one way of doing fitting, which was interesting because it also provides the uncertainties in the profile and the gradients, was to use this Gaussian process regression, which has been done by many people before, but applying it to in a general way to all of jet data took a bit of extra time to figure out how to do. But the advantage now is that you have these smooth profiles. They match the experimental data quite well, and also the uncertainties quite well. And now we can just pick different radial points on all these profiles, get all the plasma parameters from that radial point, and then use that as an input to the qualities model to generate our data set. Now, if you do this with the experimental data, so I took this is basically a collection of, I think, nearly 1,200 discharges, 13,000 time windows from about 2,000 discharges at JET, just automatically grabbed from their database and sampling the parameters, the dimensionless parameters which we use as input to qualities. And the interesting thing here is that we can see the distribution, so where the experiment lives in this, kind of conceptual dimensionless parameter space. And that's, you see that in the hollow bars, basically the black ones. And then the orange ones tell us where the turbulence model predicts a stable configuration so that there is no turbulence, right? And as expected, we see it at low gradients, right? Low gradients in temperature, ion temperature, electron density, also the impurity densities, and low Q, low magnetic shear. It's all the expected stuff, but it's nice to see it, here. Of course, you need to know a lot in order to expect that, but for us, it was nice to see it. But it's also not the only visualization you can do with these distributions. But there is one caveat here, is that they are one-dimensional distributions. So any correlations between parameters gets lost in this visualization. And that's something that the neural network, because we give it all the parameters at once, will hopefully be able to capture internally. But the visualization of it is very difficult. It's one of the challenges with machine learning and big data, is how do we visualize it? But okay, we're working on this as well. I think I'll skip this one. But then the idea is that now I have trained the neural network. So if we've included 14 parameters now compared to the 10 from before. And these are just some slices in this dimensionless parameter space to see how well the networks are performing. And we see the old ones in blue. Don't mind this, is because the data was clipped for the old networks so that it didn't have these points. So that's why it kind of goes flat. But we can see that the blue networks, where the experimental data exists, so parameters that are reasonable for a machine, the performance of the network is quite good. But if we go into a set of parameters where the machine doesn't have any data, so we basically have no data on, then the machine learning network doesn't predict anything very well. And so we wanted a way to kind of automatically detect this. Like, when are you outside your training set, so that you can flag somebody who's running the model to be like, hey, okay, this simulation is starting to deviate from where it was trained. You may not want to trust these results, like, initially. And one way to do that was to do committee networks. And now committee networks are basically just individual networks, but all combined together to give a gathered prediction. So then you get some statistics on your networks. You get a mean and basically a standard deviation. And we can see here from the standard deviation of this collection of networks, if you're outside of your training space, then you really get, you really see that the predictions of the network start to differ from each other, your variance gets bigger, and that was one way to indicate that you're in an extrapolation space. And we can hopefully use this as a parameter to, flip the simulation from the neural network to the original model and back and forth. So we still get some of the effect of the speed up of the model, but without having to trade off the accuracy when you're outside of your training set. So I guess that's it. This is just some results, the same run done by my colleague before. And we can see that, yes, the performance of the network is quite good, at least under this condition. So it's matching the original model very well. The price we pay, though, unfortunately, is because of the added networks and the added complexity is now it takes about 15 minutes to run 2 seconds of plasma. So we're trying to improve that as well a little bit, but it's not so bad. It's still quite reasonable. But that's about it for me. Hope that was educational.
Yeah, that was very interesting. And wow, the speed up is very impressive. I guess that's to be expected, but.
Yeah, well, I mean, it's not trivial that like it would have been that fast. And actually, if we use a faster transport model, so the one that I show all these results from is actually like a more robust but slower transport model. There is another one that we have put our networks into, which is more of like a bare bones transport model called Raptor. And then we can get, 1 second of plasma. It would take less, like, I think it was what, 0.8 seconds of actual wall time. So then we can predict faster than the plasma actually evolves in real time. And that has also a lot of applications if we can, prove that it's accurate, has applications in control oriented algorithms. So you can kind of put it in the control room, evaluating the plasma's next steps before it happens so that you can do something to avoid something, right? And that is really nice. Yeah.
Very promising. Well, the floor is open for questions. If, as you said, if you're through with the presentation. So feel free to unmute yourself.
Hi, Aaron. This is Matt Carr here.
Hello.
Can you say a little bit about the topology of the networks you're using? Like how many layers and how much connectivity?
Yes, so our networks, at least the ones that I've shown you, this 10D and then this 14D that I'm working on, are purely feed-forward neural networks, fully connected. It's 3 layers of about 150 neurons.
Okay, that's quite small.
It is quite small, but we found that this was sufficient to describe the problem because there's only 14 inputs, and the space like the topology of the output space, let's say, is not that volatile. So in essence, we actually think we're putting too much, but we have found that, okay, if we reduce it to to like 50 neurons per layer, you take a bit of hit on the RMS error and loss metrics for the networks. So we're not sure if that's necessarily a bad thing because maybe it's not overfitting anymore, but we're not sure also. So
and how did you generate the population for the community polling? How do you get because if you've got the same data set that you're training all 10 networks on, is it just you change some hyperparameters and then you get a subtly different?
So no, it's in those cases, what we do is we do a random initialization. Okay. So when we start the neural network, it has to have some value for the weights and biases.
Right.
And we just pick them to be completely random for each of the 10 members. And because of that and the stochastic gradient descent algorithms, it ends up in a slightly different local minimum. So each of them are in a separate local minimum, but because of the flatness of that minimum, they still produce relatively the same results where there is a lot of data to constrain the optimization.
Okay. And in terms of the software, were you able to use one of the off-the-shelf solutions, like you was using TensorFlow or, yeah?
Yeah, so
Okay.
the original 10D model and even the 14D model are using TensorFlow. But we have some master students here who are starting to use Keras, which is a bit more user-friendly, but it's still based off of TensorFlow. So, and they're having good success with it as well. So it's something I have to learn.
Okay.
Yeah.
All right. Thank you. That's all from me.
Yeah. Thanks for the questions.
So there's a question in the chat from Deval. It reads, my question regards the amount of knowledge that has been needed to do this. As in, is it a lot of physics or a bit of data science or vice versa? I think I had a similar question too, so we might pack it together. You mentioned during your presentation that you had to take some physical consideration in the design of the neural network. So maybe you could give us a few more details on this aspect.
Yeah, okay. For sure that it's not trivial, the amount of physics that you need to know in order to, you know, produce a good result from these neural networks, because it's not obvious where it comes in, right? When we look at data, so if I were to show you this plot here, right? If you didn't know this set of parameters was a reasonable plasma in a machine, and then this set of parameters was not a reasonable plasma in the machine, you would spend a lot of time trying to get this to be correct, but maybe it's not necessary, right? So that's like, from a very general standpoint, that is where the physics comes in. Also knowing exactly like, okay, what happens if I'm off, like, see, even here, the heat flux is off by maybe, you know, 20%. Is this good or bad? Is it too much, right? And because of how we know this model interplays with the transport models in general, we know that, okay, as long as it's not zero, it's actually quite good, because this will bring the gradients down towards this side, and then the actual steady state solution, or the solution the plasma will find, lies around here. So you don't really need such good high accuracy here. It's why Carl in his original networks decided to clip these points out, because they were giving him troubles in fitting this area by forcing the network to try and get this right. Right. So that type of physics knowledge is not trivial where it comes in, but you do need it to sort of judge whether or not the network is doing what you want and whether it will perform and produce results that you want. But in terms of actually how it inspires the architecture of the neural network itself, is that in the microturbulent world, there's different modes. So in this case, like ion temperature gradient modes, electron temperature gradient modes, and trapped electron modes are the main ones that we care about here at the DIFR, at least. And they basically, what we know is that the mode is either unstable or stable. So all of the transport phenomenon that results from a certain mode turns on and off all at once. But if you fit these variables independently, so heat flux and maybe particle flux and momentum flux, what have you, independently as independent neural networks, they might get this switching of where the on and off is slightly different. And then when you put it into the full transport model, sometimes one quantity will start transporting while the other ones are not. And that turns out to be really, really bad in the model, because it throws your simulation off completely. So that kind of forced us to say, okay, is there a way we can constrain that they all turn on and off at the same time, even though we're training them independently? And one way that we found to do it was to just change the outputs. So now the outputs is, instead of just particle flux, is particle flux divided by heat flux, such that when the heat flux turns on, all of them turn on at the same time, right? Because then you multiply by the heat flux. And if the heat flux is 0, then all of them are 0, right? So stuff like very, like that's a very basic concept, but it was like in terms of what we had to do, but it turns out to be crucial. Things like that you would only get by knowing, let's say, sufficiently the plasma physics and the turbulence phenomenon, right?
Sounds like a fun exercise.
It is. It's also very frustrating because when you're sitting there being like, oh, we need to constrain it this way, but how do we make that constraint? Everyone's sitting at the table staring in space, trying to figure out like how do we put this into the code, right? So it's fun, but also frustrating. Yeah.
So you did mention it takes quite some time to train the network. Was that like a few weeks or months?
So no, it actually, so we can train the network. Well, okay, so my experience, so I have about 12 million data points, and it takes me about 4 to 7 hours to train a network on a supercomputer with 16 cores. So it's not prohibitively long, but it can be if you are doing this trial and error and figuring out, okay, this network needs to change a little bit. We have to change some hyperparameter somewhere slightly. It can be a bit tedious, but it's not prohibitively long by any means.
Yeah, I guess you do multiple trials.
Yeah.
Before you get it right. But say you had, okay, you have like the best transport model, or say like the state-of-the-art transport model that you're going to use to control ITER. But then as ITER starts working, you have new discharges, maybe that contain new physics that you want to put in the model. So would you have to retrain the whole thing if it say the whole thing took you a lot more time than 8 hours because you used eventually, I don't know if that makes sense, but I'm making the case up. You use like all the data available from all tokamaks ever, like the relevant data, and it took you so long that would it be possible to like just sort of add knowledge to sort of extend the training, so to say?
Yeah, so there's this concept in the machine learning field of what is transfer learning is what it's called. And effectively what that is just taking like how there's layers in the neural network, taking the first few layers and fixing them so that they're not updated, and only updating the last, 2 or 3 layers, such, or 1, 2, or 3 layers, such that with new data. So you retrain with only the subset of data that you want to add, but you only allow the machine to change, the machine learning algorithm to change the weights at the very end. And the concept and how we think about this is sort of each layer of the machine learning of the neural network in this case learns some features of the input space. So learn some features from the one before it and tries to simplify or reduce the amount of information into only what it needs to make the prediction, and it gets less and less each time, or more and more important each time, each feature that it comes up with. But the idea is that the first few layers of features are general to the whole problem, and only the last ones are specific to the problem you are trying to tackle, right? So we would say, like, we would hope, like, we've never tried this with our neural networks, but we could say that, okay, the first few networks or the first few layers kind of capture, general plasma behavior or general plasma turbulence behavior, that if you have certain types of gradients, then you're going to get turbulence. Whereas the last one maybe tell you exactly what type of turbulence or exactly what small phenomenon happens in there. So if you get some new physics that's not like completely a new mode, then it could be captured by something like transfer learning. But of course, to know whether that's applicable or not, you'd have to study the new data, right? So
Is that something, is that a fairly new concept, or is it something that's been going
I
on
mean,
with transfer learning?
new, not new, I don't know. I think that's probably like the first time I heard it was maybe 3 years ago. And I'm pretty sure it's existed in the machine learning community for longer than that. Because they did this for classification networks that try to tell, you know, like cars from people or dogs from cats, right? So they found they could take, when they trained on dogs versus cats, they took the beginning of the network and then trained the next layer with, let's say, horses. And then suddenly it was able to differentiate horses because they all have similar features, but it's just the final thing that tells it whether it's a horse, a cat, or a dog is all in the last layer, right? So
And maybe I'm getting over my head here, but do they ever talk about like interference between those sort of new layers of knowledge? Like, can you, by adding that some knowledge, sort of degrades the predictive power of the fixed layer?
yeah, I think this is I mean, I haven't, I can imagine that it's like in my experience, I've definitely seen this happen where if you focus too much on one region of, let's say, the space, the prediction space, then you lose the capability to predict the rest of it, even if you have data there. So it's definitely a danger that if you provide too much information of one type of scenario, that you can bias your prediction to only look at that scenario or only predict that scenario. And that's one of the difficulties why like we can take a lot of a lot of lessons from, you know, just computer science in general. How do we, and data science, how do we make sure that our data set is representative of all the different scenarios we want to capture without being biased on one particular result, right? And this is work in progress. We have another master's student here who is also helping us with data clustering to figure out, okay, where do we have redundant data that we could possibly throw away, you know, some points such that we get better predictions on everything else, right? And we have some interesting results there, but nothing concrete yet.
Brilliant. Thank
Yeah.
you. I'm going to stop myself for now and ask again to the audience if somebody else has any further questions.
Well, first of all, thank you for the nice talk. And I'm super new to the topic, so my question might be very simple. Why is the discharge you were showing nice, really nice things? Was there any specific reason to choose this discharge? And on how many discharges it was tested?
Yeah, so I mean, currently we have it tested on, well, tested to this degree of fidelity on 3 discharges at JET. One of them is a high performance H mode, the other one is a hybrid, and this one is from the carbon wall. And why I chose to show this one is, well, to be honest, it's just because it has the best match. But there was no reason. So this particular discharge was chosen basically because this was the one that Jonathan, my supervisor, Jonathan Citron, he used this as his original test case for his proof of concept. So we just were, you know, comparing apples to apples and used the same thing to test our new networks and just to see if we can reproduce what he came up with. But as for exactly why this discharge, in theory, there was no particular reason. It could have been anyone, right? Yeah.
And also, maybe you mentioned what kind of validation metrics are you using, and are maybe several of them, and on what input parameters does it depend?
Yeah, okay. So in terms of validation metrics, what you see here is our ultimate validation metric. If it can produce profiles inside the full transport model that are comparable to the original model. Of course, we have metrics along the way, but they're hard to get anything concrete from, because most of the time when we deal with neural networks in general, we have a loss function where we calculate, okay, based on, you know, some criteria, how much we think that this this network scores on this arbitrary metric. And the ones we've been using so far is just root mean square error. So if we evaluate the network on all the points of the original data, what is the, you know, the mean errors, mean squared error of those predictions to the original points. And of course, that has issues as well on whether or not, you know, if you use root mean square error or just absolute error, you know, lean yourself towards one type of solution versus another type of solution. And that's why when it comes to metrics, it's very vague. So we've come up with this one where we have to finally just do the comparison to the original performance of the model in the environment that it's supposed to work in as our metric. And that has so far been sufficient for us, but it's hard to quantify, definitely. Yeah, no.
Any further questions from the audience? All right. If not, then thank you very much, Aaron.
Yeah, no problem.
Very interesting, and I think the starting point was very appropriate level-wise, and then of course we were able to bring it up to the level that everyone wanted it to be. Yeah, thank you so much.
Yeah, thank you.
And thank you all for joining us. Feel free to fill in the survey. We'd love to have you follow us on Facebook if you want to know about the next talk. In fact, the next talk will be on helicon plasmas on March the 12th. We'll be posting that. And I wish you all a very pleasant end of this day.